Water is more dense than benzene. Let me write water here. Then we have benzene. Alright, so water is more dense than benzene. So if we have a separation flask that looks like this, okay, water will be at the bottom. We call that the aqueous phase. Alright, then benzene will be at the top. We call that the organic phase. Essentially, in this experiment, we want to see the degree at which benzoic acid, which is going to serve as our solute, saturated solution of benzoic acid, once introduced into the system, has tendency to be partitioned in the organic and aqueous phase. That is distribution. We want to know the extent, the number of association N of the benzoic acid in the organic phase and in the aqueous phase, and also to determine its concentration by titrating with 0.05 sodium hydroxide. Alright, so that is essentially what this experiment is all about. Benzene and water are immiscible, meaning they can't dissolve into each other, they can't combine, they can't just associate into each other due to their differences in polarity. They have differences in polarity. While water is a polar substance or a polar compound, benzene is non-polar. Alright, and polarity has to do with dipole moment, different charges on the oxygen and hydrogen atoms. So when a solid benzoic acid is going to be serve as our solid. So when a solid such as benzoic acid, which possesses polar and non-polar characteristics, we know that benzoic acid looks like this. Benzene ring attached to the carboxylic. Okay, so this is what benzoic acid looks like. This portion you can see here is the organic portion of it, carbon hydrogen. This portion is said to be non-polar, but this portion of the benzoic acid is polar, and that makes it possible to be associated or distributed in the organic phase owing to the benzene ring, and in the aqueous phase owing to this polar group, oxygen and hydrogen. So oxygen bears a net negative charge, hydrogen bears a net positive charge. So we have a difference in polarity. So that's why benzoic acid is actually suitable in this experiment. So when the solute benzoic acid, alright, is introduced into a separating flask, like I've said earlier, looks like this, alright, with a stopper, alright. So when benzoic acid introduced into this separating flask containing two immiscible solvents, we know the two immiscible solvents, water and benzene, alright. So when benzoic acid is introduced into this separating flask containing these two immiscible solvents and shook, you have to shake for like 30 minutes, okay? The solid benzoic acid gets distributed between these solvents, alright? And now this distribution, or the ability of this benzoic acid to distribute between these two immiscible solvents, is dependent upon the solubility, alright, of the benzoic acid, how soluble this benzoic acid is between the immiscible solvents, alright, depends on the solubility. And I've said that earlier, based on the polarity, benzoic acid is slightly polar and non-polar at the same time, alright, and that is why it's able to distribute itself between this organic phase and aqueous phase, as I've said earlier, alright. So we have what is known as equilibrium constant. So at the distribution equilibrium, alright, at the distribution equilibrium, the concentration of the benzoic acid, which is the solute, and the two solvents, benzene and water, alright, is the same at a given temperature. So that is that's how we get to involve what is called the distribution equilibrium. Okay, now this constant, the concentration of the benzoic acid in the organic phase and its concentration in the aqueous phase is the same at a given temperature. So it's a constant. So that is what we are trying to say here. All right. And this constant K is what we call distribution coefficient of the benzoic acid, which is the solute between the two immiscible solvents, which is the benzene, organic phase, and water, aqueous phase. So just get this straight. So in a nutshell, we have what is called a chemical potential. All right. So the chemical potential of the solute of the benzoic acid, okay, the chemical potential all right, of the benzoic acid, all right, in the immiscible solvent, like I've said earlier. And this immiscible solvent must not react, okay? The immiscible solvent must not react, because if they do react, then we have a problem, okay? Now, what is this chemical potential? This is the symbol micro, right? What is this chemical potential? The chemical potential is actually the energy attributed to the removal or addition of a molecule, all right, from a given system. The energy attributed to the removal or addition of a molecule from a given system, all right? So, and the system here we're talking about is the separating flask. That's just general definition for chemical potential. But in this experiment, all right, the chemical potential refers to the change in energy. Okay, right? The change in energy when a molecule of benzoic acid, all right, is transferred from one phase, all right, to another phase. So is the change in energy when a molecule of benzoic acid is transferred from one phase to another phase, right? That is just the chemical potential, all right? So the chemical potential of benzoic acid now in both phases, that is the aqueous phase and the organic phase at equilibrium, all right, are equal. So the chemical potential of benzoic acid in the organic phase is equivalent or equal to the chemical potential of the benzoic acid in the aqueous phase. So we have something like this, and we have a relationship for chemical potential. So chemical potential, which is micro, is RT ln A. Okay, so that means we can have that of the organic phase. We can just have ln A 0 is equals to RT ln A aqueous. Alright, so the chemical potential in the organic phase is equivalent to the chemical potential of the benzoic acid in the aqueous phase. So that is just an expression, and it shows that there is no net transfer of the benzoic acid molecules between the two phases. This is actually when there's no net transfer between the benzoic acid between those two phases, okay, at equilibrium. All right, so with that being said, let me give another expression. So in a nutshell, I said the chemical potential of the benzoic acid in the aqueous phase or in the organic phase, then A, let's have an O, organic phase, is same with the chemical potential of the benzoic acid, all right, in the aqueous phase. So what does A mean? A means activity, right? Activity of the benzoic acid in the two phases. And then in this experiment, we could liken activity A to concentration. We want to know how much of the benzoic acid, at equilibrium. Yeah, right? So then T, we all know, is temperature. temperature, while this is the molar gas constant. It's a gas constant, okay? So in summary, the partition coefficient K, we know that concentration of the benzoic acid in the organic phase and the concentration of the benzoic acid in the aqueous phase is a constant, right? And which we call the partition coefficient, right? So partition coefficient of benzoic acid in the organic phase, benzene, and the inorganic phase, water, is given as, have a general formula, log CW equal to 1 over n log C0, alright, plus log K. This is a general expression, right? This is log of the concentration of benzoic acid in the water, alright, or you say in the aqueous phase, alright, 1 over n log concentration of the benzoic acid in the organic phase plus log K. And you could see that this is equivalent to a straight line equation, right? So we can see this is y, this is mx, meaning that this is the m, right? So this is m and m is slope. Your slope is equivalent to 1 over n. So here we could actually get to know the association number due to the benzoic acid in the two phases. So when we plot a graph of log CW against log C0, our slope is equivalent to 1 over n, alright? Then we have log K, which is our intercept, alright? From here we could be able to find the distribution coefficient or the partition coefficient using graph from our graph, alright? You can also find K by calculation, alright? I will also explain that subsequently now, alright? So that means if we could have a graph like this, we can actually have a graph like that looks, plot a graph of log CW against log C0, whatever, however the graph is going to look like, okay? Bear in mind that your slope is equals to 1 over n. Then you can find the intercept, alright? When you plot the graph, you should be able to say if the graph is going this way or it's going that way, alright? So, but I wouldn't tell you. So slope is 1 over n, okay? And your intercept, wherever it might be, alright, is your K, alright? Is your K. So, and that is that. So what is this association number n? Alright, it refers to the degree of dimerization of the benzoic acid molecules, alright, in the benzene phase, alright. It gives us an idea to the extent the intermolecular interaction of the benzoic acid happens or takes place in the solution, alright. So, and that is that. You remember that benzoic acid is serving as our solute, alright. We just made a saturated solution of the benzoic acid to serve as our solute between the two immiscible solvents, right? So I'm going to use an example to explain how you're going to carry out this experiment. Alright, if you get to look in your table, you are told that you're going to prepare some mixtures. You are given a table, but I'm going to pick up where the funnel 1, alright, you have something like funnel 1, alright. So you're going to prepare a series of mixtures, alright. The funnel 1 data that said that the benzoic acid, you take 10 centimeter cube, and then the benzene you're taking okay, benzoic acid, I think you're taking 40, right? Then the benzene you're taking 10 centimeter cube, that's 10 volume, 10 mil, right? And then you're taking water, distilled water, 50, right? That's if you look at the column that had to do with how you're going to the funnel number 1, all right? Benzoic acid 40, benzene 10, water 50, all right? So what does that mean? So you're going to have a burette where you can collect these volumes, exact these volumes, okay? And you're going to introduce these second volumes of the solution, all right, into the separating flask. So you have a separating flask, okay? Separating flask looks like this, all right, with a stopper, all right? So you're going to introduce benzoic acid 40 ml, benzene 10, and water 50, All right. So once you've introduced, be sure that this lower end is well tight, right? It's well tight, and you need to ensure that you have a stopper that is very much good, that wouldn't cause you to lose some of the solution or some of the volumes of either of these reagents. Okay, so once you've introduced it here, all right, you close the stopper, you close it and shake for 30 minutes. So you're going to shake for 30 minutes. All right, and why are you shaking? You want to establish an equilibrium at room temperature. All right, so once you've shook for 30 minutes, the benzoic acid, which is the solute, all right, should be able to get distributed between the organic phase and the aqueous phase. And you know why I'm putting the organic phase at the top? Because it is less dense, right? Benzene is less dense than water. Water is more dense, so it settles at the bottom. All right, so we shook for 30 minutes so that we establish an equilibrium, right, between, for benzoic acid, between the organic and aqueous phases. All right, so, and after doing that, you have to clamp it. All right, you have to clamp it. So we have a clamp, you have to clamp it, allow it to stand for like 20 minutes or even more. Right, so, and after doing that, you have to provide yourself with some other flask where you have to drain off the lower end, which is the aqueous phase. All right, let's say this is the system we're going to collect our aqueous phase. So you drain off the aqueous phase. All right, so the intermediate, there is usually an intermediate here, you don't collect that one. All right, you will see just an intermediate layer between the organic phase and aqueous phase. You don't collect that, so you collect only the aqueous phase into a separate flask or a separate containing vessel. Okay, so once you've collected that, you keep it aside, label it, okay, and you label it based on maybe 401 or whatever, however you want to label it. And then you have to discard the intermediate layer. All right, you have to discard it. Let me make this diagram look more clearer. Okay, let me make it look more clearer so that you understand this. So this is a separating flask, right? Okay, so we have the organic phase, which is the benzene layer. Then we have the aqueous phase, which is the water layer, right? So this is a stopper, a cover, all right? So there's a control tap here, okay, before you get to collect your solution into a system, a labeled one, right? So, and then you have a stand where you clamped it to stand for extra 20 minutes so that equilibrium is established for the benzoic acid and the two immiscible solvents. All right, so like I said, you have to collect the aqueous layer separately into a separate container. Okay, once you've collected it, I said there will be an intermediate layer here, so you have to discard it. All right, so once you've collected this, you have to open the tap again such that all of the intermediate layer is discarded. You remove them, we don't need the intermediate layer, and what you'll be left with is the organic layer, which we need. All right, so that is how you treat funnel 1. All right, so the next thing you're going to do is you're going to before then you should have a system. What I mean by system, a burette filled with sodium hydroxide. You're going to run the titration. We want to determine the concentration of the benzoic acid in these phases. Okay, and be making use of a burette. The burette will contain sodium hydroxide of known concentration, standard solution of known concentration of what's it called, sodium hydroxide. Okay, so now let's treat for the organic layer now. All right, so for the organic layer, you're going to pipette. All right, you're going to withdraw 5 ml of the benzene layer, which is the organic layer. All right, and add 20 ml of distilled water. All right, so you're going to add that to, let's say, the system, a Lumiere flask. All right, so you take 5 ml of the organic layer, into add 20 ml of distilled water to it, then phenolphthalein indicator will be used. All right, so and you're going to titrate. All right, you're going to titrate. So essentially you're going to get volume of the base needed to actually neutralize that of the organic layer containing the benzoic acid which you've just collected. So you take 5 ml of the organic layer, add 20 ml of distilled water to it, then titrate. Run your titration. All right, so the end point is usually pink. All right, from colorless to pink. All right, so the same thing you're going to do. All right, so after getting result, the volume, so you're going to run this 2 times. All right, you run duplicate. You're going to run it 2 times. Okay, so that means you're going to collect this aliquot or this portion from the organic phase 2 times, and you're going to run the titration 2 times. So you're going to have some values for the volume. All right, that is essentially what we need. We need the volume, all right, of the base. Do you understand? So the same thing you do for the aqueous phase, but for the aqueous phase you're going to collect and titrate 25 ml of the aqueous phase. You're taking 25. All right, so once you've introduced 25 ml of the aqueous phase, then run again using sodium hydroxide, concentration of around 0.05 molar. That's concentration of the sodium hydroxide. Okay, we know the concentration, but we don't know the concentration of the benzoic acid in either of these phases, and that is why we are running this titration. We want to know the concentration of the benzoic acid in the organic phase, all right, and also in the aqueous phase. You see, so we want to know the extent of distribution of the benzoic acid in either of those phases by carrying out this titration using sodium hydroxide, known concentration, and using phenolphthalein indicator. So once you run for the aqueous phase, the same thing, colorless to pink. Pink is the endpoint. Okay, so you collect 25 ml of the aqueous phase, run it, the same setup. All right, do duplicate titration too, because you're going to need an average. You're going to make use of an average. All right, so let's go to how you present it in form of table. How would you present your result, and how are you going to do the calculations? All right, so how would you present your result? That is the next thing. Right, and if you remember, I've been explaining this based on funnel 1. All right, we are treating funnel 1, how you can report it. So you do the same thing for funnel 2. So if you like, you can have a table that has this data funnel. All right, then you have average titer. All right, the average titer for what? The organic phase, right? Then the average titer, please, I'm using 80 for the aqueous phase, like that. So we're going to have an average titer for the organic phase and aqueous phase. All right, I've explained that previously, right? So I'm going to have molar concentration of what? Of the benzoic acid in the organic phase. So I'm going to have CO, right? Then I'm also going to have the molar concentration of the benzoic acid in the aqueous phase. I'm going to have CW. You see that? So, and you can actually get to have a table that shows the distribution coefficient. All right, you can have K, and then let me say we have another column for K, right? So we have this column, this column, this column, this column, this column. We can still have another column for log C concentration of the organic. So whatever you got as the molar concentration CO here, we take the log. And we're also going to have log concentration of the benzoic acid in the aqueous phase, that's CW. So you see, you need to have this in your table. You see, so how would you now get these parameters? Average titer, I said you run for each of those phases, you run 2 titrations. So you're going to have average titer, let's say x1, you got something, the volume of the base required, okay? plus x2 divided by 2. Whatever it gives you is the average titer for the organic phase. The same thing here, x1 plus x2 divided by 2. Do you get it? So how would you find the molar concentration of the benzoic acid in the organic phase? And that is pretty simple too. You can make use of this formula, M1 V1 plus 2 N2 V2. Now you can say this is the organic layer. For the organic layer or for the organic phase, we want to know how to quantify the concentration of the benzoic acid in the organic layer. So what does M1 mean? This is for the organic layer and this is for the sodium hydroxide. So let me make it more clear. So I have M1 V1 of the sodium hydroxide, okay? Then M2 V2 of the organic layer. So what is M1? The standard is a standard solution. The concentration 0.05. If you check your manual, that's the concentration of sodium hydroxide that will be prepared. So, and what was the volume of the sodium hydroxide needed? That is your average titer for the organic. So your average titer will be here. Can you see that? So your average titer for the organic layer, all right, multiply by that, okay, then equals, what is M2? M2 is this, which is the concentration, all right, of the benzoic acid in the organic layer. So we can substitute this to be C0, all right, can you see that, times V2. What is V2? V2 is how much of the volume of the organic phase did you take? You took 5 centimeter cube, remember. So here is going to be 5 centimeter cube. All right. So it's going to be that. All right. Unless you want to convert and all of that. So, and this is the average. Do you get it? So from here you should be able to get molar concentration C0. Can you see that? So that is what you do for funnel 2, funnel 3, funnel 4. So how would you get that of the aqueous phase? The same thing. All you have to do, write an expression. So we have the aqueous layer. How much of the aqueous layer did you take? You took 25. Remember, you took 25, and here is going to be CW, right? So this still remains, but the average titer should be due to that of the aqueous phase that you took in running the titration with sodium hydroxide. So the same thing, you should be able to get this value too. Can you see that? So once you've gotten it, then you're almost close. You can have the log of the concentrations, the log of the concentration in the organic phase and the aqueous phase. Then before you get to plot your graph, so you're going to have a series of values that would help you to actually plot your graph, okay? So this is essentially how you get to carry out this experiment, okay? And don't try to lose the solutions. If your stopper, what I mean by the stopper, that's the separating flask, is not so tight, request for a very tight one so that the solutions don't go out, and be sure that this is well tight. All right, so then you get to have your values, plot your graph, find your K, all right, from the graph, or you can do that by calculation. Remember, C0 CW is a constant, which is the distribution coefficient. So that's essentially how you carry out this experiment.